So before installation, I'm going to check what Ubuntu release that I'm using. So to do that, I'm going to open up a terminal and type this in. Okay, so the version that I'm using is Ubuntu 20.04.1 LTS. All right, so to go to the GitHub repository, I'm going to open up a web browser. So the link for the repository should be in the description box below, but in this case, I'm just going to type it up. So it's github.com/fadila-wahudi/FineMAV. All right, so this is the home page for the repository. I'm just going to zoom in so you can see a little bit more clearly. And over here is the README file. And if you scroll down, all the way to the bottom, it says we recently released the GUI version of FineMAV for Linux. So to find out more information about how to install it and to launch the GUI version, please visit our wiki. So I'm going to open that link up. So now we're at the GUI version page on the wiki. So this is section 5, and we're in this part of the wiki. So in order to download it, it says we need to click here to download the GUI version. So I'm going to open a new tab for that. So as you can see, it has redirected me to the Google Drive link. So right now I'm in a Chinese-speaking country. So this is all written in Chinese, but this basically means download. And it says, would you still like to download this file anyway? Yes. We're going to save that in the desktop folder. So as you can see, it's downloading right now. And I'm just going to open the progress bar so you can see the progress. So this should take a few minutes depending on how fast your internet speed is. All right, now that it's done downloading, I'm going to close these two tabs here and go back to the wiki page. So next it says I need to give the file executable permissions. So to do that, I have to copy this command. So I'm going to go and navigate to my desktop folder. And if I do ls, this is what it looks like. So if I go here, I need to give permissions. So I'm going to copy this command and paste that here. So now it should turn green. Okay. The next part is to launch the GUI. So I'm going to copy this and paste that here. Okay, so this is what the GUI version should look like. I'm going to make it larger so you can see. So over here would be the required flags, like your input file, your prefix, which is the prefix that is assigned to the output files, then your reference genome. And then over here below would be your optional flags. All right, so if we scroll down, it says refer to the running FineMAV page to find the checklist of fields that need to be included in the input files. So I'm going to open that up in a new tab. And so this is the checklist of fields that need to be provided. So this would be the chromosome number and position, the ID field, the reference allele field, alternative allele, ancestral allele, the CAD-FRED score, and the allele frequency for the alternative allele. And then this would be done for each population. So we've actually provided some test files for you to try out. And the test files can be found in this repository in the test files directory. So first we would need to clone the repository. So to do that, I'm going to go ahead and copy this link here and go to the terminal. I'm going to open a new tab. We're still in the desktop folder, and I'm going to run that. So this should take a few minutes depending on how fast your internet connection is. Alright, now that it's done, I'm going to ls to see what's inside. So over here we have the GUI version, and here would be the FineMAV repository. So it then says I need to navigate to the test files directory. So I need to go copy this command over here, paste that, enter, and if I ls to see what's inside, you can see that these are the files and folders that are in the repository. And over here is the test files directory. So next part is to navigate to that directory. Okay, and if I ls, this is what is inside the, just put that up. This is what is inside the directory. So these are all the test files, but for this video, we're just going to focus on one file right here called the vcf_allfields.txt file. And the reason why we're focusing on this file for today, or for this video, is because it contains all of the fields that we've mentioned in this checklist over here. So we're going to open that up to see what that looks like. All right, so this is what the vcf_allfields.txt looks like. Yep, this is the whole file right here. And what I'm going to do is I'm going to go through each of the column one by one so you can understand what's inside. So the first row is the name of the header, and the next few lines would be the data. So if we go to the first column, it says chromosome and position. And so this one here would represent the chromosome number, and this would represent the position. And as you can see, it has a colon between the two. Next is your ID field. So most of the time, this would be your DB SNP reference number. Next is your reference allele. So this is the allele that is found in the reference genome that you're using. Next is the alternative allele. So this would be the non-reference allele. Next is your ancestral allele. So the ancestral allele is the allele that is found in the common ancestor, and in humans, these are inferred by aligning the genomes of multiple primates. Next, we have the CAD-FRED score. So the CAD-FRED score represents the Fred-scaled combined annotation-dependent depletion score. So this is a score that predicts how deleterious the alternative allele is. And if we scroll all the way to the right, okay, let me just zoom out so you can see. Okay, the next three columns here are the allele frequency for each of the populations. In this case, we have POP1, POP2, and POP3. So this program can recognize any number of populations, And you can also change up the name if you want to. So you could change this from pop1 to, let's say, Bob, or cat. But for this run, we're just going to stick to pop1. All right, so that is the vcf_allfields.txt file. We're just going to close that. All right, so next what we're going to do is we're going to run the program. So we're going to go to the GUI version, and if you scroll down here, it actually gives you an example of how to run it. So the input file should be the vcf_allfields.txt file. So if we browse there, go to FineMAV, go to test files, go here and open that. That should link it to the input file that we need. Next is the prefix. So the prefix, we're just going to make it test run. So like I mentioned earlier, the prefix is the prefix that is going to be assigned to the output files. Next we have the reference genome. We'll just make that HG19. And next is the VEP file. So the VEP file is to supplement information that is not in the main input file. So this will actually be discussed in another video. But because this text file contains all of the fields that we need to run it, we don't need to supplement it with a VEP file. So we're going to go ahead and run this. All right, program completed successfully. So this is what's printed out as it's running the program, and it will tell you what stage is on as it's running. So now we're just gonna close this, and we're going to check out what the output files look like. So if we just go back to this, and okay, so these are the output files that the program has produced. So we're going to go through them one by one. So I'm just going to open up the text reader. So if we go back here, you can see that we have the log file. Then we have this thing called the testrun.txt file. So that is a file that contains all of the intermediate calculations and the FineMAV scores. Then we have these files over here with .bw. So these three are the bigWig files, and these can be used to visualize the scores on a genome browser. So we're going to check out the log file first. Okay, so let me just, all right. Let's just drag this so you can see. Don't want it too large. Okay. This is the name of the input file. As I mentioned, it's vc_allfields.txt. The name of the VEP file, which is none. Then we have the reference genome, and then we have here the chunk size. So the chunk size option is used if you want to run a large data set and you want to save RAM. So it will run the data set in chunks. And each chunk will read a specific number of lines. So in this case, the default number of lines is 200,000. Next, we have the penalty parameter. So this penalizes the allele sharing between populations. So we've just opted for the default version. Next is the number of SNPs, which is 11. Then we have this number of SNPs where the ancestral allele either does not exist for that SNP, or either the ancestral allele is the reference allele, or the ancestral allele is the alternative allele, or for that SNP, that ancestral allele is neither the reference allele or the alternative allele. Next, we have the number of populations. So we have 3 populations, pop1, pop2, pop3. And then this log file then reports the maximum FineMAV score for each of the populations. At the bottom, it mentions how long it takes for the program to run. Next, we're going to open up the testrun.txt file. So this contains the intermediate calculations and the final FineMAV scores. So as you can see here, the first row are the names of the field, and we're going to go through them column by column. So the first part here is the chromosome and the position. So as you can see here, they're actually been separated into 2 columns. Next, we have the ID column, which we talked about, the reference field, the alternative allele field, ancestor allele field, and then the CAD-FRED score. So that would be all in the input file. Next, we have the allele frequency for the 3 populations, POP1, POP2, and POP3, which is also mentioned in the input file. So just scroll over here. Next, after the allele frequency, we have the DER. So the DER, DER, represents the derived allele. So the derived allele would be here. The next 3 columns are the derived allele frequency for each population. So this will be the numbers here. If we scroll over to the right, the next part says sum of DER. That is the sum of the derived allele frequencies from these 3 populations, and this would be this number over here. Next is the DAP. So the DAP is a measurement ranging from 0 to 1 that shows how spread out the derived alleles are between the populations. So if the value is 1, that means that the derived alleles are found in a single population. If the values are closer to 0, that means that the derived alleles are evenly spread out throughout the whole throughout all the populations. Next, we have the final 3 columns, which is the FineMAV score for the 3 populations, and that will be these columns right here. The FineMAV score is calculated by multiplying the CAD-FRED score, the derived allele frequency of that population, and the DAP here. Okay, so now that we've gone through the log file and the intermediate calculations / FineMAV score file, we're going to go talk about the bigWig files, the 3 bigWig files that you see here. So in order for you to see it, what we can do is upload it onto a genome browser. So I actually have a genome browser that is on my computer, and it's called IGV. So I'm going to go ahead and launch that. So this will take a few minutes for it to load. Alright, so this is IGV. So we're going to go open up the File Explorer and navigate to the desktop folder. And as you can see here, these are the 3 bigWig files. So I'm going to upload that one by one. Alright, so these are the 3 bigWig files, and the hypothetical SNPs are in chromosome 1, so I'm going to go zoom in there. So the axes are not the same, so I'm going to change the axes so they are the same. I'm going to open up the log file, and it says here the maximum FineMAV score is for POP3 is 1.2, which is the highest out of all 3 of them. So I'm going to make the axes 1.3. Where is IGV? Okay, so I'm going to change the data range for these 3. Set data range to 1.3. Sorry, 1.3. And just gonna set that to maximum, and then change the height of the track to 100 so you can see it a little bit more clearly. And this is what it looks like. So these are your values for POP1, POP2, and POP3. So if there are any spikes in certain parts of the genome, it may be worth investigating. So thank you so much for watching this video. If you have any questions, please comment down below and I'll answer them, and thank you.